But now if you have an application, a compound expression is made up out of the original things and the variables and all of that by square brackets there. So how do you remove a variable from a combination f of g? The answer is, well, why didn't you remove it from f first and then remove it from g and then put those together by s? Because if I brought the variable in again, it would get back to where it was supposed to be. So that's what s does. So s allows us to remove a variable from any f of g combo there. And so this is lambda calculus done by combinators here. So changing to a combinator, some combination A with respect to variables x, y, and z, that's lambda abstraction in order, lambda x, lambda y, lambda z. Not everybody uses the period in there. I like to use the period there to kind of separate the variable from the expression I'm working on. But it's just a notational convention. It doesn't really mean anything. Okay, so you see, if you want to remove variables, you have to say from what combination, but you have to say in what order you want to remove the variables. And we do it by working at the right-hand most variable first. And then do it. Question?
Yeah, is that an exhaustive pattern? Will that match all lambda expressions and then allow you to transform them into
S's and K's. Yes. Yeah. Because the syntax is just variables or constants and square brackets. That's the only syntax we have to work with. And so the algorithm that I told you there looks at all possible syntactical things that can come up and goes to work on them. If that's the only syntax you have, constants, variables, and square brackets, then those are the only rules that are needed in order to read that syntax. You see, I have a big expression here. I parse it. So what it's going to happen there? It's going to be parsed into several pieces there, and you'll be able to see it as something, square bracket, something, unless it just has come down to a single letter, okay? So then you do that first square bracket, and now you have lots of other square brackets to face, and now you do it again, and so forth. But the syntax is only the syntax of application, f of x. Yes? Does that make sense? Yes, in the back. Louder. I still couldn't hear, honey. Okay. I was sneaky there to sneak in another rule that says if you're trying to remove the variable v from f of v, if you're trying to remove the variable v from this combination here, where v does not occur here, okay, then we're going to take the cheap answer there and saying removing the variable v where there's no v here to be looked at is just that. So that's called the eta rule, and I'll talk about it later in terms of the model. So it's just a tidiness there. It's stupid to have an extra v there if it doesn't occur in this. Question? Please.
So we're saying that the variable doesn't affect the output of f, and so that's why we can remove it?
Yeah.
Okay. So we're removing variables that don't affect the output of the functions.
Yeah, so let's see. Let me do an exercise here. Can you see the board from where you're sitting?
Yeah.
Okay, I'll write over here. So what if we took f of v and we want to remove the variable from that? What will we do there? Well, I would have to look at this part and this part here. Okay? So when I remove the variable from this part, I have the identity function. Lambda v of v is the identity function. Oh, sometimes I write it as j, never mind here. Now I use that extra rule here. There is no v here, so when I remove the v from that, I have f there, but I need to combine them by s. This s comes in here because I'm focusing on that pair of square brackets, okay? So s of f of identity function is the function such that if you apply it to a variable here, you distribute the variable over there, and I won't write it down because I'm very lazy here. I of v is v, and so we're back to where we started. Make sense?
I'm struggling.
Why are you looking puzzled like that?
I'm struggling with it.
You have to replace the s by s is defined. You can arrive at what you just said.
Removing variables is kind of distributing. I'm undistributing. So when I undistribute the v out here, I have to write an s. And when I take it out of here, I'm free to just say f here because there's no v's to worry about. When I remove the variable from this, I have I left over. And now I have undistributed the v to the outside. And so now s will say, well, if you want to put it back, you'll get back to where you started.
Starting to get closer.
Okay. So, I have a number of combinations here that we can try out. Of course, it's trivial, as I was just saying, if you remove the variable x from the single variable x itself, you just have the identity combinator. If you remove x from x of x, you have SII. We saw SKK earlier. That's turned out to be the identity combinator. SII is a very dangerous combinator because it's self-application. And self-application was the cause of the Russell paradox. So you have to be careful of how you use it. Okay? Now here's another thing. You can reorder the variables however you please there. So originally I I eliminated variables from the composition combination x of y, x composed with y applied to its argument z there. And it turned out that that elimination gave me s of k of s of k. Okay? But now suppose I eliminated the variables in a different order. Of course, you'll get a different combinations of s and k. And this is where it becomes grungy, because the longer your combinations are, the more s's and k's you need. But we'll try it out here. I'll just test this one here by using that combination that I just said here. And now let's see if I can apply it to the C rules. Oh, okay. I'm getting just a little bit tired here, so I'm going to be very sneaky and say, let's keep doing it until it stops. Mathematica allows you a very abbreviated notation. Apply your rewrite rules once, or apply your rewrite rules over and over and over and over, and over again. It's just a backslash that a slash, not a backslash, a slash that does it. Terrible kind of syntax in Mathematica sometimes, but once you get used to it, it results in very short expressions. You have to be awfully careful of doing the rules over, the conversion rules over and over again, because some combinations don't stop rewriting themselves. But it did in this case. Okay? And so I can test these things. I don't think I have to do it there. It'll work out. How many of you actually have Mathematica to use? Oh, a few of you. Okay, well maybe you can get a friend to help here, because you'll have my notebook and you can try it out and you can make up your own formulas there. I did it into PDF, and unfortunately it's an extremely long file, but it's all there. It's I made a PDF copy of the thing.
What would you recommend as a free Libra alternative to Mathematica?
Just a second. What was the question again?
What would you recommend as a free and Libra alternative to Mathematica?
A free alternative?
There is none.
I don't really think there is one.
Just for this.
I wouldn't be surprised if you could do a lot of these simple-minded things in Haskell, actually.
Wolfram does have an online product.
Okay, we're coming to a new era. Cloud computing is going to completely change our lives, right? You won't have to have your own copy of the software. You're going to be able to do the computing in the cloud. So I think there are things. Of course, you may have to pay a smaller fee to do a few computations, but it's certainly going to be a blessing, because who knows what machine you're working on there. So it's better if you can do the computation in the cloud. So here I'll just do, here's a sort of triple composition, okay? And there's where the S's and K's start coming in, right? So if we want to test that on that, we have to try to test it, and I'm going to cheat here by doing it all at once, not going through the separate steps there. And oh, it didn't get rid of that there. Okay. I thought it would get rid of it here. Oh, I see. Okay, I applied the rules there. Oh, I know why. Because the test that I was making had only 3 variables in it, but the original problem had 4 variables in it. So that's why I have to do it again with the 4th variable. I left out the 4th variable, but when I do it again and follow the rules all the way to the end, it didn't get rid of everything. Oh, stop that. Sometimes I hate computers. I think I did things in the wrong order there, and I eliminated the variables the wrong thing. So I think I messed up there. It really should work that original long expression at the top of the page there, when you apply it to 4 variables, x of y, x, y, z, w, it will eventually, when you distribute it across there, it will give you that original combination. So I'm just going to stop in a minute here after I do this very important thing. Here is a use of self-application. F of x of x, where x is the variable there, and f is a symbol, nothing, x doesn't occur into it, and so eliminating the variable x gives me that combination. So now if I apply that, take the test of applying that combination to that, and I have to do it a couple of times here. Do it again. Ooh, I better do it a couple of times there. Okay. We get that. And so the answer here is that this combination that I came up with, this combination when this combination is applied to itself, you get the eliminating, it has no variables in it, because the combination had no variables in it. That was just the combination that I found here, the first step there of self-application. But now, if I try to reduce that combination, you see the symbol f, which is just a constant for a function there, appeared there. The symbol f appeared there, and it was embedded into those s's and k's. And now when I do it, I have to do it a couple of times. And now, if you could read that, and only machines can read these things here, we have f of the original combination. In other words, we're able to find a combination involving f, combination p involving f, which when we reduce it by these reducing rules, reduces to f of the same damn combination. Every function has a fixed point. Kleene didn't realize it at first. He did recursion by search. Recursion means to run backwards, if you know Latin. Recursion means run backwards. Curare is run. But you can also run forwards there by saying, okay, do it once, do it again, keep doing it until you see something nice and then stop. You can run both forwards or backwards. So search is very often done by running forwards. And Kleene used search for doing recursion in his original thesis there, and of course afterwards there. But Curry realized self-application gives you the fixed point. This is a recursion equation that says P is defined recursively in terms of itself, and so we'll see how that is here. We just have to be careful. If I kept doing this over and over again, I would get f of f of f of f of f of f of the combination if I did it over and over again. And if I kept doing it, I would be getting f of 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 f on infinitum. So you have to be very careful. This immediately gives combinations that don't reduce in any finite number of steps. But it's still very interesting that when we reduced it a little bit, we could interpret it as a fixed point of a function. And I'll make a lot of use of that. Okay.
Question?
I'm just thinking a little bit here. Question? Yes.
I'm still not sure what the fixed point is. I see that you can go infinitum, but what's the definition of a fixed point of a?
Save that question until the next session, okay? Where I show it in terms of the model. Then you'll see what it is. Okay. I think we're making fairly good progress. I'll just give you a couple of examples here about normal forms. Normal form means when you do the rewrites eventually stop transforming the things. Did you have a question? Yes, over there.
So in this case, f was the successor function. How do I interpret the fixed point? Because
Yeah, I'll have to show you that in terms of numeric functions, so postpone that question until later, okay? It's a good question. I mean, this is very, very bald thing here. It doesn't show you how you want to use that, okay? So I'll answer that question later. Another question? Okay, so what I say is if you were so lazy as to only take combinations of k's, you'd never get into any trouble, because any combination of k's will be reduced eventually to k of 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 k. Okay? Why? Let's prove that. Okay? So suppose you have a combination that only involves k. Well, what it's going to look like when we parse that expression, it's going to start out with k of something, of something, of something. That's the only way you can parse square brackets there. Okay? Now, if we apply our rules to that, that first segment, k of a1 of a2, is just going to reduce to a1. So I've reduced the original expression with one application of the rules to a shorter expression. And it's expression of the same kind, just masses of k's. So therefore, I'm back to a shorter expression. If I keep doing it, it'll get shorter and shorter and shorter until you get to k of k of k of k of k, in which case there are no rules to be applied. So we do have normal forms there. Okay, and I did some tests there. I'm sorry, I'm getting just a little bit tired, and I think a break will be here. I gave a paper in the thing there. I give tests here of certain combinations of S's. Mathematica allows in mathematics itself to do recursion there. So I say, let's form combinations of S's and S's over again in a certain pattern there, indexed by integer n there. And so I gave tests there that those combinations settle down pretty nicely. However, an arbitrary combination of S's is not guaranteed to have a normal form. And so I gave examples and tried it out there, but better, if it interests you at all here, this chap, Waldman, he gave a proof so that you can test a combination of S's as to whether it is reducible or not. There's no test for the full combinator calculus as to whether an arbitrary combination of S's and K's has a normal form. It's a recursively enumerable, non-recursive set. The expressions that have normal form are recursively enumerable because you just apply the rules until you find the normal form. And so that's, you say, hey, it's good. But if it's never going to stop, you can't guess whether it will stop or not. And so that's an example of a recursively enumerable, non-recursive set of expressions. So he showed if you restrict attention to S itself, there's actually a horrible decision method for whether it has a normal form or not. So if you're interested, you can look that up. So I'm almost having to stop here, if I can get my screen to come up here, because what I'm saying here is to go from combinators to lambda calculus, what we want to have are the rules that say, first the rule alpha that says bound variables, the lambda operator, the S's and K's have no bound variables in them. But lambda calculus has bound variables, and it's much easier for humans to use with bound variables. So the alpha rule is alphabetic change. If you're careful not to confuse free and bound variables, you can alphabetically rewrite x as y. Something we always do in first order logic, for example. The second rule, named by Curry, is the beta rule, which says if you have removed a variable from an expression and you apply it to an argument, and now from now on I'm going to be using round brackets for application, since I'm not going to use Mathematica anymore. If I apply a lambda abstraction to an argument, I just substitute the argument into whatever it was that I was abstracting out of. The reason that it's called the beta rule is that beta is the second letter of the Greek alphabet. It has no metaphysical significance. Alpha is perfectly good, alphabetic rewriting, but beta is just there. Now, I actually implemented in Mathematica the eta rule, which is if you eliminate x from f of x, it's just f there. It's a nice rule, but I'm not going to use it anymore, even though many people use it there. A weaker rule is if f were obtained by eliminating variables, then, of course, if you put the variable back in, you'll get back to f. And this is really related to saying that if two combinations are the same for all x, then when you eliminate the variable x, you'll have equal combinators. I much prefer that, and we'll see how that works in the model there. Okay, so question?
Yeah. Can you explain free variable and bound variable?
You have to say louder, please.
Can you explain the free variable and bound variable? What's the
Yeah, sure. I'll give an example. Okay. So I'm taking lambda x of f of g of, lambda x of lambda y of g of x and y, okay, and f and g are constants, okay, and I've eliminated variables from two combinations, the whole one and the internal one there, okay. And now suppose I say, let's apply this to h of y. Your friend from the other laboratory said here is, oh, you have that good combination there. Will you please apply your combination to my h of y there? Now, if you just put it in for x, this x here will have to work on this part here, okay? If you bring it in, you'll get f of, square brackets, lambda y of g of h of y of y. And your friend says, I don't think that's right. Why is that wrong? It's because this y is external here, and this is just a bound variable. I could have put the bound variable as z, okay? And now when I bring this in for the x, I'll have z, and now that's correct. The other time when I did it, I confused two uses of y's. That's the problem. This is a free y, and this is a bound, this was a bound y. And when I just blindly brought things in, I confused a free one with a bound one. And it is the wrong meaning. Because if I put a fresh variable in here, then you can see these two places are not linked, But if I'm too stupid in doing my rewrites, I would be linking things that shouldn't be linked. That happens in first order predicate logic all the time with quantifiers. You have to be very careful of which variables you use when you're making substitutions. Other question? Please.
The way you wrote this lambda and lambda x, there is a little bit of confusion if the application of h and y is inside this lambda expression or not.
Well, the problem came with this binding thing here. This binding of the first x, that's going to work good. It just says, take the new argument here and move it in for all the occurrences of x.
The problem is that it's not clear that you are applying that to x or if you are applying that to f.
No. The combination invoked f here, but the combination was the whole thing.
It ends there.
Yeah. So there were no x's. There were no x's here. F is just a constant. There were no x's there, so I didn't have to worry about f. I could just write f.
Okay. This notation is not absolutely clear. But
Oh, I think it is.
Often, when I read about lambda-calculus, they would use parentheses there to make sure.
No, well, let's see. There is a problem in formal languages about prefix operators and postfix operators, okay? And so maybe it's a good thing you answer that question, because the square brackets are a postfix notation because you have that closing bracket at the end, but lambda is a prefix operator. So you have to be a bit careful about association things there. So I didn't understand your question at first, and you were absolutely right here. When you say lambda x here, you really should say the scope of the x only goes over that. Okay? So there are two solutions for this. De Bruijn decided to use lambda as a postfix operator, and it really looks weird if you do that. But another thing that people tried was to use application as a prefix operator. Need more blackboard space here. To use application as a prefix operator, so I could write lambda x of f applied to lambda z of g applied to x applied to, oh, I know no more brackets anymore. This is Polish notation without any brackets here. G applied to x, and all of that applied to z. And now, if you use Polish notation and lambda as a prefix operator, there is no confusion about association there. So thank you for asking that question, because mathematicians don't pay any attention to syntax mostly. Okay, because you say, I meant what I meant. but if you're careful about pre and postfix things there, you have to make sure that you're there.
How would you write the HY in this case?
Okay, so h of y is h of y. But what I wanted to do was apply the whole damn thing to h of y. So I put the application on there. So that's prefix notation. Let's take a break. I need a break. Oh, we have lunch! Hurrah! The point of the first session was, in general terms, to show how a few simple rules can lead to complicated behavior. And it turns out that those are rules that people have liked to use for a number of different purposes, and of course is a kind of extremely condensed form of functional programming with those kind of things. What I'm going to do now in the next two sessions is to show what can happen when you try to model these things and what kind of structures that you can get into these models that might be useful for something else. So it's modeling the lambda calculus now. And so again, the axioms for the lambda calculus are alphabetic rewrite, conversion, meaning substitute an argument in for that variable bound by the lambda. And then I did put it in the rules that in eliminating variables that I showed last time, the so-called eta conversion that says if you're thinking of f of x where x is the variable there, then lambda x f of x just means the same as f. Now, I'm not going to assume that rule completely. I'll assume a weaker version of that rule in my model I'm going to show you. But it's also easy to get other models where that rule could be put in. But it's not really important there because it turns out that the same expressions can essentially give you the same functions, and this kind of rule really doesn't either buy you anything. It doesn't cost you very much to include it, but it doesn't really buy you anything there. And so I'll show you why I don't assume that rule in a minute. So the lambda calculus in Church's formulation is an equational theory where, of course, replacement of equals by equals is assumed because that's how you do equations, but these are the special axioms governing the lambda operator. Is there any question about what kind of formal system this is?
So when you say axioms, but each of them is an infinite family of
Oh, sure.
axioms, right?
So by the dots there, I meant any well-formed expression you can put in there, right? And so if you have a well-formed expression with the variable x in there, and you be careful not to capture free and bound variables, and you rewrite that variable in that same well-formed expression by a y, then you want to mean lambda x blah of x is equal to lambda y blah of y, where the blah is supposed to be the same on both sides. Question?
And so the square brackets just denote input.
No, the square, now, okay, thank you for doing that. I had to use the damn square brackets for Mathematica because Mathematica uses square brackets for functions and round brackets for algebra. Like when you write 3x plus x squared, you have to use round brackets in algebra. So that's why I use square brackets here. Here, this is more informal there. It just means I'm thinking of an expression, okay? The square brackets don't have any meaning in themselves. I'm just saying I'm thinking of a well-formed expression that's made up out of doing things like this. If you have an expression, you can always put any lambda in front of it, okay? If you have two expressions, you can always apply one to the other. Sorry. That's the syntax here. One variable binding operator, one application operator. And I apologized before that I didn't pay attention to the difference between a prefix operator and a postfix operator. So you should be a little bit careful to make sure you know how the scope of the variable is in there. As I said, my good friend Dick de Bruin wrote the lambda on the other side so that he have a postfix notation, but it's horrible to read. Question?
Yeah. So like lambda in a language like Scheme or a language like an anonymous function in JavaScript, right? What's the difference between the lambda operator here and like a Scheme lambda or like in a practical implementation of it?
Wait until we get a little bit further, and then tell me what you think after we get a little bit further.
Cool,
Okay?
Cool. Yeah.
They're supposed to be related. McCarthy was a student at Princeton. He actually did differential equations. There was no computer science in the early days. He did differential equations. And then later on, he and, I'm blocking our names, I always blocking names, started talking about what artificial intelligence should be. Of course, Turing earlier had talked about thinking in terms of artificial intelligence. And then when McCarthy and his group developed Lisp, they took things from Church's lambda-calculus. But McCarthy writes specifically, he read the first few pages of Church's monograph, but he never really understood it. But he got the idea that something like a lambda could be helpful. And of course, it's very important in Lisp, as you all know. But he didn't really understand it when he did it. But it worked, thank God. I knew him very well, so I can say things like that about him.
May I make one more question too? And I know you already said what the dot was, and you said it was kind of arbitrary, but what is the dot again exactly?
No, the dot just makes a separation between the variable and the expression within which you are binding the variable. It's just to separate.
Okay.
Separate the variable from the part you want to get bound up.
Gotcha.
And it makes it a little bit, some people just write everything all together, and I find it harder to read. So it's just a convention to sort of space things out, okay? Now, what I'm going to do is build up a model here. One thing about the lambda calculus is it consistent? It's an equational theory. You can just do formal proofs there. Is it possible, using the equations of that theory, so that you could prove any expression was equal to any other expression? That would be a kind of inconsistency in the sense that everything collapsed. Okay? So is the lambda calculus consistent? Or going back to the combinators of S and K have certain rules of reduction. You could also read the rules backwards to expand. So suppose you take combinators and you reduce and expand and reduce and expand. Could you prove any two combinators are equal to each other by reductions and expansions like that? Could you prove that S is equal to K? It's not possible. But if you do it completely syntactically, it's a very long proof to prove that it's consistent. Okay, I'm going to give you a model where the consistency will be immediate because the rules of lambda calculus are valid in the model. The combinators have the right properties in the model. The model is non-trivial, so therefore the rules don't collapse. Okay, so the universe that we're going to have here is the power set of the integers. You know what the integers are. Take all subsets of the integers. The power set of the integers is going to be the model. How in the world could something like the power set of the integers work for combinators? It doesn't seem like they should be related. Well, the trick is, just as Gödel showed us in his original incompleteness proof, integers and integer arithmetic can mimic any kind of complicated syntax. Integers can be code numbers for complex structures, finite structures, of course. Okay, so I'm going to do a little bit of Gödel numbering there. The first one there says, a pair of integers can be immediately represented by a single integer just by saying, well, every integer can be factored into prime factors. So of course, there's a maximal power of 2 when you factor the integer, and then the quotient is odd. Okay, so any power of 2 times an odd number is uniquely associated with the n and the m on account of what you know about unique factorization. So we have a one-to-one correspondence between pairs of integers and the positive integers. 0 is left out in this coding. There are many different ways of coding pairs. This is rather wasteful because it's exponential, but it's the shortest one to write down, I know. Okay? It doesn't matter. We're not really worried about complexity here. So I'll use iterated exponentials without worrying about that. Now, if you can do pairs, just as in Lisp, you can use pairs of pairs of pairs of pairs of pairs of pairs of pairs to represent sequences. So now the empty sequence can be represented by 0. And then if you do a const of adding a term onto the end of a sequence, you just take the pair of the first initial segment of the sequence and that extra term that you've added on. This gives a one-to-one correspondence between all integers and all sequences of integers. So sometimes we write it as thinking this way with this kind of coding here. I can think of n here as being the same as n star using Kleini's notation from automata theory, all finite sequences of integers, and the integers are identified there with the 8 of the Gödel numbering. Okay? So that's a very little bit of Gödel numbering. One more step, and there's also other ways of doing it. Any sequence could also represent a set, just the set of terms of the sequence. Of course, that's a rather wasteful enumeration because many different sequences would represent the same set. So if you want to be clever, you can find a one-to-one correspondence between the integers and the finite sets of integers. But I don't have time. I'll use this wasteful one, but it's perfectly good. And now, the general Kleini star operation here, of which this is a special case, if I have any set of integers, then x star is the set of Gödel numbers of the sequences that represent finite subsets of x. So you can read x star as I'm thinking in terms of a Gödel number of some finite subset of x, and I can decode it from n there. Okay? What I'm going to try to convince you of is I could teach this stuff to juniors. You just need a little bit of arithmetic, a little bit of set theory. There's nothing that's hard to understand in this. But now for the next step, we'll see what you think, if we can understand it here. Oh, I put in an extra part here, there, just to remind ourselves that recursive arithmetic was originally proposed by the Norwegian mathematician in the early 20s, but it was after the Hilbert School got on to formalization of metamathematics that a very serious study of recursion was done by Rózsa Péter from Hungary. And Ackermann, one of the key things, of course, was primitive recursion. Primitive recursion is just a recursion where you go from n to n plus 1. But there's double recursion and there are other higher recursions. And Ackermann, the student of Hilbert, already in 1928, gave a very simple double recursive function that was not primitive recursive function. And so quite a lot was understood there. By the time Gödel started his thesis work, a lot was understood about kinds of recursive definitions. However, what Gödel shows in his incompleteness theorem is that primitive recursive functions are extremely powerful, and all kinds of syntactic transformations can be defined via Gödel numbers and primitive recursive functions. Primitive recursive functions are very powerful, even though Ackermann showed that a double recursive function is not necessarily primitive recursive. But Gödel showed how much you could do with primitive recursive functions. And sometimes we forget when discussing recursive enumerability because we are brainwashed by Turing machines, if you'll forgive me for saying that. But primitive recursive functions tell you what recursive enumeration is, because you can think of a primitive recursive function as saying, oh, I have a lot of Gödel numbers representing finite structures, let me set up a primitive recursive test to see whether that finite structure is kosher or not. If it's not kosher, I give the answer 0. If it is kosher, I look at it and say, oh, it contains M. That's a very significant output. So a single primitive recursive function can do lots of syntactical analysis on Gödel numbers. And every recursively enumerable set is just basically the positive range of a primitive recursive functions. You kick out 0 as meaning the testing failed, but when you say a positive result means the testing is okay, and then you read off what the output was. Every recursively enumerable set can be given by choosing the proper primitive recursive function to set it up. You don't need Turing to understand it. Turing was a genius. I wish I could have met him, but I don't think we need Turing machines as much as we say. And I'll see if I can convince you of that. So now let me go back to my universe here. The universe is the power set of the integers, and it has a very simple topology. Now, sophomores, or definitely juniors, should have had some topology from calculus. The topology on the power set of the integers is easier than the topology on the real numbers. We say a neighborhood of a possibly infinite set is determined just by a finite subset. You just give a finite amount of information about a possible set, and then you have a neighborhood of all those sets which share that same information. And this gives a very nice topology. There is a stronger topology, which is sometimes called the product topology, where you not only give a finite amount of information about the set, but a finite amount of information about the complement of the set. And sometimes we speak in terms of the topological space 2 to the n. That's the product of 2-point spaces infinitely many times, and that's a compact Hausdorff space. I'm taking just half of the topology on the product topology here. This topology, using only finite subsets of the set themselves, is just half of that. Of course, sets are represented by points into 2 to the x by means of characteristic functions. 0, you're out of the set, 1, you're in the set, and so on. So the power set of the integers and 2 to the n are very closely related, but there are 2 different topologies there, and I'm taking the easier topology. Disturb anyone to talk about topology? Can I answer any questions about that? Please.
Could you give me an example of 2 sets that would be in the same neighborhood?
Sure. Right? Think of any finite set. Okay? Like, think of your telephone number. Okay? Now, there are infinitely many sets that contain those given finite ones. That finite telephone number determines a neighborhood, and any other set that contains those finite number of elements is in that neighborhood.
Okay, thanks.
Other questions? Okay. Now, once you define topology, you need to define continuous functions. Now, we torture our students in calculus with epsilon delta definitions of continuity, and the main difficulty in understanding epsilon deltas is that there is a combination of 2 quantifiers in writing down the definition of continuity. Here, I can say it in an easier way. I can say it completely in words here. A continuous function of several arguments, this is a continuous function from subsets of integers to subsets of integers. A continuous function, a function of several arguments, is said to be continuous if and only if a finite amount of information about the function value is already determined by a finite amount of information about the arguments. Let's see what it says here. A finite subset of the function value is already completely determined by some finite amount of information about the arguments. And if you think in terms of your course in the calculus and look at the epsilon delta definition, finite amount of information are usually done by rational intervals, and so a continuous function is such that a rational interval around the function value is already determined that the function will stay within that rational interval by a rational interval about the argument. And you can rewrite that in terms of epsilons and deltas. But it's really exactly the same definition. Now here is the key thing in this model. If I look back, where did I? Oh, I see. Okay, maybe I have these in slightly different order. It doesn't matter. Okay. I took these from another lecture, and so they were a slightly different order. So I haven't told you yet what the application operation is here now. The universe is the sets of integers, power set of integers, and I'm going to make this universe into an applicative algebra here. First, I'm going to define application by a certain formula there, and then I'm going to reverse that formula to define lambda abstraction. So here is the way this works. And people use, in fact, it's a well-known phrase from recursive function theory. They're talking enumeration operators. Enumeration operators are just the continuous functions on the power set. You can think of it this way: input and output. As you're enumerating the finite amounts of information about the input, you go through some mumbo-jumbo to enumerate the finite information about the output. That's what another way of reading what continuity means. Of course, the question is whether the mumbo-jumbo can actually be carried out, or whether you need some godlike creature to do it for you. But you can think abstractly of input and output. As you're collecting a finite amount of information about the input, you're outputting, extruding finite amount of information about the output, from the input to the output. So we're going to just do that in terms of Gödel numbers here. That's what that formula says. If I don't fall over here. Think of the set F, set of integers, as a lookup table. So start enumerating the finite subsets of X. Look at what Gödel numbers you need to mention a finite subset of X. Now go to the lookup table and say, Mr. Lookup Table, did you allow n to go to m? Mr. Lookup Table said yes. And so you say, oh good, I can now output m as one integer in the result. And so the more I know about x, the more I'll know about f of x by this definition.